Welcome to another UK-SPS seminar. Today we have Adam Morrison, who is Associate Professor at the Blavatnik School of Computer Science, Tel Aviv University. His research is on the security and the performance of shared memory multiprocessors, from microarchitecture through operating systems to algorithms. His work has been awarded the Internet Defense Prize, the Intel Hardware Security Academic Award, several Best Paper Awards, including ones at Unix Security Symposium, and also ASPLOS and the Micro. He also received the IEEE Micro Top Picks and Top Picks Honorable Mention distinctions. Today, he's going to talk about speculative type of vulnerabilities in the wild. Now I pass the stage to you.
Okay, thank you very much for the introduction and for having me. So I am going to talk about speculative type confusion vulnerabilities in the wild. This is joint work with my student Ofek Kirchner that was published in the Unix Security Symposium this year. So if there are details that I gloss over, and there will be, you can check out the paper for the full details. And just let me say that please feel free to interrupt me and ask questions. If there is something that you want to ask about, don't wait until the end. So this talk is going to be about speculative execution attacks. You probably heard about them. You heard the name Spectre and Meltdown. You probably saw all the headlines in the newspapers in 2018. So this talk is going to be about that. I will give a brief background about exactly what they mean. But before I proceed, let me just give you a kind of executive summary of what I'm going to talk about. So like I said, this talk will be about speculative execution attacks, specifically about an attack called Spectre Variant 1, which is popularly known as a bounce check bypass attack. I'll explain exactly what this means in a minute. This Spectre Variant 1 is a unique vulnerability because there are no hardware mitigations for it. Instead, the CPU vendors just state in the documentation that software developers should mitigate the vulnerability in software. So it's important to understand how feasible it is for software developers to do these types of mitigations. And in this work, we observed that many software mitigations target explicitly bounce check bypasses, which is really the way that Spectre Variant 1 was popularized. But there are other ways that Spectre Variant 1 can be exploited. So we set out to see if such alternative vectors exist in the wild, and we actually found out that they do, and that they can be quite insidious to mitigate. So the takeaway will be that the current approach of putting Spectre V1 mitigation burdens on software developers alone might require rethinking. It's probably not as simple as just saying, be careful about bounce checking of array accesses. So I'll start with some quick background about Spectre Variant 1, so we are all on the same page. Spectre Variant 1 is the class of speculative execution attacks that exploit conditional branch misprediction. They are often characterized as bounce check bypasses, and this will be the example that I use in this slide as well. So the goal of the attack is to exploit speculative execution in the CPU, exploit speculative execution of a certain code gadget in a victim program to obtain information located in the victim address space, which is not otherwise accessible to the attacker. So what happens is that the attacker controls some value X that the victim code verifies is within the bounds of an array. And then the victim code, the victim gadget, uses this value X as an index of an array access. After doing this, the victim leaks the data that it read over a microarchitectural covert channel, like in this example where it makes a data-dependent cache access. So let me pause here for a moment. Is everybody familiar with the concept of cache side channels? because this is essentially what is going on here.
Sir, we are familiar with cache memory.
Cache memory. Okay, so for the purpose of this talk, what you should know is that when you have a victim program and an attacker program located, running on the same machine, on the same CPU, or on different CPUs of the same machine, if a victim makes a cache access that where the address depends on a secret value, like here, when the address depends on the value y, then it's possible for the attacker to use their own cache accesses to infer the value y. I'm glossing over a lot of details and caveats, but for the purpose of this talk, this is what you should assume. That if an attacker is able to make the victim access the cache with an address that depends on some secret, then the attacker can afterwards get this index and learn the secret. And this is basically what's going on here. Okay, from the victim's perspective, it doesn't think that it's accessing a secret because it made a bounce check. So a correct execution of the victim doesn't do anything risky here because it reads from an array within bounds and then uses the value that it read as an address. So that's all okay. But in the context of speculative execution, what the attacker can do is they can cause this victim code to execute the gadget multiple times, passing it an inbound value of x. You see a valid x, which will pass the check. This will train the branch predictor hardware unit to assume that when this if condition happens, the CPU will assume that it's going to be correct and speculatively execute the instructions that come afterwards. So then the attacker can, after this training happens, they can call they can get the function to execute by passing it an out-of-band value of x, which would be the address of some secret in the victim's memory, minus the index of the array. And then the CPU would do what is called a misprediction. Because it thinks that this if condition should be true, it will start speculatively executing the instructions after it, which will cause the array access to be out of bounds, reading the secret. And then here the secret would get leaked through the cache side channel. And I'm not going to go into the details, but the attacker can use the fact that this instruction happens to recover the value y, which is the content of the secret, afterwards. Okay, so this is the basic Spectre Variant 1 attack.
Sir, is the Spectre Variant 1 a type of virus?
No, it's what is called an information disclosure attack. So you need an attacker to actively run it. It can happen through a virus, but it doesn't necessarily have to be.
So, sir, like with the Spectre Variant 1 secret attack, can we know the contents of the program by attacking it?
Yes, yes.
So, like, is it some sort of malicious code or what?
So this code is benign code. It's just an array access in the target program, which has bounce checking. But there is some malicious code running on the same machine, which has access. It can invoke this code. I will give an example of how something like this can happen in a minute. It can invoke this code, passing it inputs, and get it to execute, to mispeculate, and therefore misbehave. But this code itself is benign code. It's trusted code. So let me give you an example of how something like this can happen. Think about the case of an operating system kernel as the victim and of an unprivileged user running as the attacker, right? Because the operating system kernel does not trust the users and the processes. So specifically, we looked at the Linux kernel. So what can happen here is that you have some function which is called from a system call, or maybe it's a system call itself. Users can trigger system call execution in the kernel. So an untrusted process can cause this function to execute in the kernel context, passing it this out of bounds pointer to a secret, and by doing this, be able to read some secret value in the kernel address space, which is not otherwise accessible to processes. And why is this a bad thing? Because the kernel address space has all physical memory mapped. So by exploiting Spectre against an operating system kernel, against the Linux kernel, an attacker can basically read any address in physical memory, which means they can read address spaces of other processes, of the operating system. They can read anything in the machine memory. Okay, so is the context okay?
So, sir, like with the Spectre variant one attack, an attacker can get access to physical memory locations of the program and the data?
If they're attacking the kernel, yes.
No, if they attack the kernel, okay. Like, okay.
Yes, exactly, yes. So what can be done about Spectre Variant 1? It uses a very basic mechanism of modern CPUs, which is speculative execution. So the crucial point here is that although the attack exploits the branch prediction mechanism in the CPU, it also requires the victim program to contain a vulnerable code gadget, like we saw in the example. So perhaps because of this, the hardware vendors did not fix the issue in hardware. They don't want to disable speculative execution. Instead, they are directing developers to change the software and add protections to prevent this type of attack. So what do these protections look like? So let's take Linux, for example. What they have done is developed a manual mitigation approach where they require kernel developers to use a special API in vulnerable code gadgets. So whenever in Linux there is an array access where the indexes can potentially come from an untrusted source, Linux developers have to know and use a special API to perform the array access. They don't do a normal access in C, but they need to do this special API. And internally, this API takes care of protecting from the attack. It makes sure that the array access remains in bounds even under speculative execution. Okay, so that's the way that Linux tries to solve this problem. Notice that it only works for these types of attacks, attack vectors like I described, where the attacker is attacking an array access with bounds checking. But the problem is that in general, Spectre Variant 1 is defined in the original paper as any attack that exploits conditional branch prediction to make the processor temporarily violate program semantics by executing code that would not have been executed otherwise. So this means that bounds check violations are just one example of Spectre Variant 1. There can be other ways of making the program the program execute incorrectly. And therefore we ask, if the software mitigation is tailored for bound check bypasses, does the system remain vulnerable to some other Spectre vector? And in this work, we explored whether Linux is vulnerable to a different vector called speculative type confusion. This is a different type of program semantics violation in which the CPU misspeculation makes the victim execute with some variables holding values of the wrong type. And this is what causes secrets to be leaked, to memory content to be leaked. So let me give you an example of a case of speculative type confusion. So consider this C function, which will be part of the kernel code, and it implements some form of data inheritance. The argument that it gets is a base type, and the function derives a specific subtype using the type field. So the type field tells it what exactly the subtype is. If the argument has a type of type 1, then the code looks like this. It casts the base object to a type 1 object, and then leaks some value stored in the object. For example, just by using it as an array index, like I showed you previously. So speculative type confusion would occur if the attacker can cause the kernel to invoke the function with an object not of type 1. And when this happens, the branch misprediction will cause the code to leak the content of some 32-bit value stored in the past object, possibly leaking secret data. So if the attacker trains this branch to always be executed speculatively, like we saw previously, but then invokes the function with an object that is not of type 1, an object of type 2, then what happens, these instructions will run speculatively and a value from the object of type 2 would get leaked. And this might potentially be a secret value. Okay, so this is why it's called type confusion. The code here assumes that it's working with an object of type 1, but speculatively the attacker gets it to work with an object of type 2. So our key driving observation in this work is that speculative type confusion might occur not only in this type of polymorphic code like I showed you, it can actually occur even without the programmer realizing it. And motivated by this observation, we set out to determine if the Linux kernel is vulnerable to speculative type confusion. We found both exploitable and latent vulnerabilities, which currently seem to be unexploitable, but only by chance and not by design. So we discovered that attackers can introduce speculative type confusion into the Linux eBPF subsystem, that the compiler might inadvertently introduce speculative type confusion to kernel code, and also latent polymorphism related vulnerabilities. So I'll start by describing the attacker introduced speculative type confusion exploiting eBPF in the Linux kernel. So eBPF is a Linux subsystem that enables unprivileged processes to load sandbox programs into the kernel. So an eBPF program is written in a special language called eBPF bytecode. It can be loaded into the kernel with a system call. Once loaded, the kernel verifies that the program is safe to execute using static analysis. And this verification also adds Spectre Variant 1 mitigations to the loaded program. But again, it only adds mitigations for bounce check bypasses. And finally, after going through the static verification and adding of mitigations to the code, the program is compiled by the kernel from the original eBPF bytecode into native x86 code, and then it runs inside the kernel. And this has many uses for profiling and network monitoring. It's a very popular subsystem. It has its own conferences. It's a really big feature of the Linux kernel, this ability to load untrusted code into the kernel, have the kernel verify that it's not doing anything security malicious, and then run it inside the kernel at very high performance and with access to the system. The problem is that the eBPF verifier didn't consider speculative execution when it did the static analysis verification. And therefore, it could accept programs with speculative type confusion gadgets. And I will now show you how such a gadget looks like and explain why it passes verification. So suppose that an eBPF program with the following code is loaded into the kernel. So this is kind of an assembly code. The eBPF bytecode is some form of assembly language. I will go through this code and explain what it does in a minute. So in this code, the eBPF register R0 is initially a pointer to some eBPF array entry, which is dereferenced, and then the loaded value are loaded from this memory address into R0 is checked. If the value is equal to 0, then you see the check is that if it's different from 0, go to B. So if it's equal to 0, this line executes, and the content of register R9 overwrites register R6. And register R9 is some scalar value in the program, so it's controlled by the attacker, because remember, it's an untrusted user that loads the program into the kernel. So they can put whatever values they want in scalar variables. It's just some integer. If the value read from memory was not 0, then it's checked again. And if it is equal to 1, then the content of register R6 is dereferenced, and the value is loaded into R9 and then used as an index into an array. So essentially it's leaked. And this is okay, should be okay, because the value in R6 is a pointer to a stack, to the stack. So this is a valid memory access for an eBPF program to do. And the verifier would accept it. So this is the program. And the way that the verifier checks it is by enumerating every possible execution flow of the program, or so it thinks. So let's see what happens. So the flows that the verifier considers are as follows. The first condition, first it looks at a flow in which the first condition evaluates to false, in which case R6 is assigned to a scalar. In this case, the verifier also learns that R0 must be 0, because this if condition, the check of R0 different from 0 didn't happen. We executed this code. So this means that in this execution flow, R0 must be 0. Because of that, the verifier does not think that it doesn't need to look at this code because it's not going to execute. This code only executes if R0 is equal to 1. So this flow, the verifier is happy with. Otherwise, if this condition doesn't happen, then the verifier reasons that this code will not execute, and it starts looking at what happens afterwards. So if this code executes, then this means that R0 is 1. But like I said, the verifier reasons that this code is safe to execute because R6 is known to contain a pointer to a stack slot. Specifically, it wasn't overwritten, right? Because the verifier knows that R0 is 1. So this code didn't execute. So the verifier accepts this flow as well. And finally, if neither of the conditions execute, then the verifier is also happy because basically nothing happens. So after looking at every possible case for the execution of this code, the verifier sees that in no execution, something bad happens. They are all memory safe, and therefore it accepts the program. But the vulnerability is that the verifier didn't consider incorrect execution flows that can happen because of misspeculated execution. So the CPU might incorrectly execute the program for a while until it realizes that it's misspeculating and then start over. But while it's misspeculating, something dangerous can happen. So what's the danger here? That if we can produce a speculative execution in which the first condition is predicted to be false, so this code will execute, and the second condition is also predicted to be false, so this code will execute, we get this kind of weird execution in which R0 is considered to be both 0 and 1. So this is the flow of instructions that execute. Basically, R6 is overwritten by the attacker-controlled scalar. Then this attacker-controlled value gets dereferenced. So the attacker gets to say which memory address will be read, and then it gets leaked because that's just these two instructions that are over here. So essentially, this means that the attacker would be able to read from any address in memory. Okay, that's the basic vulnerability. Now let's look at how something like this can be exploited. So this is actually a multi-step process. What we first need to do is to load an eBPF program into the kernel that contains this speculative execution gadget. Afterwards, we need to invoke it many times in order to perform the branch prediction so that we train the branch predictor to perform the type of execution that we want to happen. Then there are a couple of steps that I won't go into for lack of time, but we use another eBPF program running on a different CPU in order to perform the cache side channel and be able to read the secret. So there is a step in which we load yet another eBPF program running on another CPU. Then we invoke the victim program that we loaded here, perform the attack, get it to read and leak the content of an arbitrary memory address, and then use our second eBPF program to actually learn the secret that was leaked and pass it back to the unprivileged user process. And the bottom line of this attack is that we implemented it and we were able to get an unprivileged process to read from arbitrary memory addresses at a rate of 6.5 kilobytes per second. So it's not incredibly fast, but it's fast enough to leak a lot of secret data. And I want to go briefly about some challenges in getting this attack to work. So the big question is, how can we create this type of speculative flow that will execute both this line and this line? And the problem we face is that these branches are mutually exclusive. So if we simply run the program many times in order to train the branch predictor, like in the early example that we have, we will never get the branch predictor to execute both of these conditions. If this one is true, then this one will be false and vice versa. We can't get them both to happen. They are mutually exclusive. So we solve this problem by a technique called out-of-place training. What we do is we allocate something called the shadow gadget in the process memory, in user space memory. And the shadow gadget has a very similar structure to the code in the compiled eBPF program. The only difference is that the branch conditions are no longer mutually exclusive. Now they are exactly the same. And this means that we can train these two branches to predict in the way that we want them. And the big trick here is that because the CPU has only one branch predictor unit, then if you put the shadow gadget in the right address in user space memory, whatever the branch predictor learns about these two branches, there will be some internal collisions in the branch predictor structure. Think about it like a hash table that goes from a branch address into a prediction. So if we can get a collision to happen, whatever the branch predictor learns about these branches, it will apply when it executes these branches in the kernel. So we place the shadow gadget in the user space memory so that its addresses in the branch prediction exactly collide with the branch predictor entries for the eBPF program's code. And then we can train it, simply execute it many times, and get the branch predictor entries to contain values that would predict this thing not taken and this thing not taken. So both of these lines will execute. And the main challenge in doing this out-of-place training and creating the shadow gadget is finding the right location in memory to place it. So we get this type of collision in the branch predictor entries. And the way that we do it is simply by brute force. After loading the victim eBPF program into the kernel, we allocate a big buffer in user space and simply try a lot of placements for the shadow gadget, training it, and afterwards seeing if the attack works or not. And if the attack works, then we are finished. If not, then we try another location for the shadow gadget. The only thing to watch out for is that this checking has to be done carefully to account for the possibility of only one branch being successfully trained, which is a scenario that still results in some leakage, but it's not necessarily the leakage of the secret. It can be leakage of the content of the stack if the code runs correctly. So we filter these cases out by changing the contents of the victim stack and seeing if the leaked value changes. And if it doesn't, then we know we have these kinds of false positive, and we keep on trying different placements for the shadow gadget, and otherwise we found the correct location and the attack succeeds. And we found that it takes us about 10 minutes on average to find a good placement for the shadow gadget. But that's not a big deal, because after you have the correct placement, you can then start leaking as much kernel memory as you want. So you pay a bit of a price initially in order to get the attack to work, but afterwards you can just leak and leak because the eBPF program remains loaded in memory in the same address. So that was the main vulnerability that we discovered, and we disclosed it to the Linux maintainers, and it was recently fixed, basically by getting the eBPF verifier to also consider speculative flows when it does the static analysis. But we found additional things which are not yet fixed, and let me now describe them. So the next thing I want to talk about is compiler-introduced speculative type confusion. So our observation here is that a compiler can inadvertently turn innocent code into vulnerable code. For example, consider this C code. Again, this would be code running in the kernel, part of the kernel. This is benign code, part of the kernel. And the structure is similar to the EBF Gadget. So it has two mutually exclusive conditions. This parameter command, it's either command A or command B. It can't be both. So because of this, when the compiler compiles the C code, it can reason that because the conditions are mutually exclusive, it might add some code here, emit some code in the first if block that moves an attacker-controlled value X to the RSI register. Basically, it's going to overwrite the RSI register in the emitted code. And the RSI register is the register that initially holds this pointer argument, which is trusted. So this means that if the attacker is able to get these conditions to these ifs to both predict true, then we get, similarly to the eBPF example, an execution in which this block will execute speculatively, overwriting RSI with the argument X, and then move on and execute this block. But this time RSI will contain the attacker controlled value instead of the pointer argument that it was supposed to contain in this case. And again, an attacker would be able to get this function to read from an address that they specify and leak its content. And unlike a bound check bypass vulnerability, here the branch predicate has no data dependency on the attacker controlled value. So it's not like in the original example where we had X smaller than something. Here the ifs don't depend on X. And the if conditions also don't depend on untrusted data. This command can be set by the kernel, so it's not untrusted. And so if a programmer looks at this code, they would have no reason to imagine that there is a vulnerability here and that they need to manually add Spectre mitigations. And this is something that we think is a big concern. It's not like an array access with bounds checking, which a programmer sees as security sensitive. This looks like completely innocent code. The big question is, does this code actually exist in Linux? Can we find it in the wild? So motivated by the observation that such code might exist, we performed a binary level analysis of Linux to find whether the kernel can be maneuvered with speculative execution to dereference user supplied addresses. What we did is analyze the call tree of every system call in the kernel, because system calls are the interface between the untrusted processes and the kernel, and they have a well-defined interface that processes can set the arguments to. And in our analysis, we explicitly did not consider if the results of a dereference can actually get leaked, because the main goal is to find if an attacker can get the kernel to read from an address they control. To actually leak it afterwards, there are many ways to do it, not necessarily through the cache, and maybe it doesn't work. Maybe you can't leak on one Linux version, but you can leak on the next version or the previous version. So the big issue here is whether the attacker can kind of break the contract between processes and the kernel and get the kernel to dereference an attacker, an address that they supply. So this is what we looked for, not the end-to-end exploits. And as you can see from this table of results, we did find that when compiling with GCC, it can introduce these type of speculative execution gadgets into the kernel. And it happened mostly in system calls that receive an optional untrusted user pointer. So I'll give you a couple of examples of how something like this can happen. And this time it will be actual code from the Linux kernel. So here is the first example. This pattern that we found is related to a register reuse optimization done by the compiler. So here we have a system call that receives an optional user pointer. This is UPTR. It checks if the pointer is not null, then it copies the data from it into an internal variable in the kernel, on the kernel stack. This is this kfoo. And otherwise, and then it passes it, so then it passes it to a helper function f. Otherwise, if the user pointer, this argument UPTR is null, then the helper is called with the null argument. And internally, the helper dereferences its pointer argument. But what happens when you look at the emitted x86 code is that the compiler did an optimization, and if the user pointer, which is initially in the RDI register, if it happens to be null, then the compiler immediately jumps to executing the helper function. Essentially, it reuses the RDI register. So what happens is that RDI also represents the first argument to a function. So the compiler does an optimization. If it sees that RDI is 0, meaning that UPTR is null, it simply calls f immediately, not passing in an explicit null value, but relying on the fact that RDI was just checked to contain a 0 value. But the problem is that if the testing branch mispredicts to jump to this function f, even if RDI is not 0, right? If the attacker trains this branch to jump and then passes a value that is not 0, then what will happen is that the CPU will speculatively do this jump and start to speculatively execute the function f, but this time with an argument that is not null. Instead, it's going to be an attacker-controlled address. And then, as we saw already several times, f might dereference this value, which the attacker will set to be a pointer to a secret, and f might dereference it and leak it. Okay? So one small note I have here is that I'm not sure if any of you studied the relevant papers about Spectre, but usually the assumption is that when the value in the register is available, like we have in this example, then a misprediction cannot happen, because why would the CPU mispredict if it already has the values and can perform the test? There's nothing that it need, there is nothing that it has uncertainty about. So why would it speculate? But we actually found that under some microarchitectural conditions, the CPU can speculate even if it has the values available. So this type of gadget is actually exploitable if there is a leak. So I encourage you to read the paper. This is a bit more advanced material, so I won't dwell on it. Another interesting gadget that we found, this time it was not exploitable, but it was almost exploitable. But the reason I want to show it is in order to underline how hard it is for programmers looking at C code to reason about these gadgets and about these potential vulnerabilities and figure out if they have something to worry about. So this gadget happens in this function, which is called from a system called keyctl. What this function does is it calls a helper function called get instantiation keyring, and it passes it the address of a local stack variable, this one. And what the helper is supposed to write some output into this variable. But when looking into the emitted x86 code, our analysis found something interesting. We see that the location on the stack for this variable is not initialized in the way you would expect. Normally, you expect stack to be initialized by decrementing the stack pointer. And what happens here is that the compiler, instead of decrementing the stack pointer, pushes a register onto the stack. And the reason it does this is that on x86, this instruction of pushing is a 1-byte opcode. And doing the subtraction is a 4-byte opcode. So for reason of space efficiency of the code, the compiler did this optimization. But the register that it pushes is a live register. It contains a value from the caller of this function, which we don't see here. And it so happens that this value is attacker controlled. It's some parameter that the process passes to the system call and happens to sit in this register, so it's attacker controlled. So now what can happen is that if inside the helper, the attacker manipulates the branches, it trains the branch predictor so that the helper returns takes some error path and returns without writing to the output variable, then what will happen is that when the helper returns, this variable will still have the attacker controlled value that it had initially. And then this value will get loaded from the stack and will be passed to this additional function that is called. And this function might, again, dereference it and leak its content. Okay, so luckily, it turned out that in this specific case, this helper function would always overwrite the output argument. So there was no kind of error path that an attacker could find that would result in the function returning without overwriting its output. But this is something that is not guaranteed. It so happened that whoever wrote this function wrote it this way, but it could certainly be that for a different function or with some different code change, this property would be broken. And this means that it's very hard to rely on the security of this code. Somebody can make a small change and it would become an exploitable speculative type confusion gadget. And then one additional thing I want to note about this issue of compiler introduced vulnerabilities is that there is a lot of room to improve in our analysis. So we did a proof of concept and binary analysis of Linux, but our analysis is incomplete. We know that it can miss certain gadgets because for reasons of simplicity, we don't explore all possible execution paths and we don't descend into called functions. And our analysis is also unsound, so it can flag something as a vulnerability even though it's not. And this is why we manually verified all of our results. But the bottom line is that I think there is a lot of future work here to improve the analysis, make it dig deeper into the Linux kernel, and I'm pretty sure that it will find additional vulnerable gadgets on top of what we found. And finally, in the time that we have, I want to quickly go over a third topic, which is how some proposals for optimizing Spectre Variant 2, mitigations, by replacing indirect branches with direct conditional branches can be vulnerable to speculative type confusion. So Spectre Variant 2 is something that I didn't talk about before. This is a different type of speculative execution attack. It exploits misprediction of indirect branch target addresses to redirect control flow to arbitrary location. So an indirect branch is where the CPU basically does a function call based on an address in memory. So instead of a direct jump, it reads an address for memory and then jumps, like when you call a function pointer in C. And this is also something, these addresses are also predicted, and if they are mispredicted, then there can be a vulnerability. So one very popular approach for mitigating this vulnerability is something called a red polling. And a red polling replaces indirect branches with a sequence of instructions that is called a red polling. And this sequence of instructions makes sure that the indirect branch is performed securely. Basically makes it invulnerable to speculative execution attacks, but essentially the way it does it is by, in a very clever way, disabling speculation. So red pollines have a very big performance impact on the Linux kernel. There's a lot of pressure to optimize them. And one approach that was suggested by Linux developers, but also by researchers, is to replace red pollines with a sequence of comparisons and direct branches. Basically, if we know that if we know the list of legal targets of an indirect branch, if we know all possible addresses that a function pointer might point to, then we would place this type of code that checks, is the value of the pointer the first legal target? If so, jump to it. Is it the second legal target? If so, jump to it. And what this accomplishes is that it restricts speculation to the legal targets instead of into any possible arbitrary address in memory. This considerably improves the performance because it again enables speculation, but the problem is that it opens the door to speculative type confusion because there is still a potential for the prediction here to be wrong, and a certain legal target address would be executed even though it's not the right legal target address. So let me show you what can happen. So the problem is related to the way that Linux implements polymorphism and data inheritance in internal kernel interfaces. So for example, to implement a common interface, specific Linux subsystems like A and B here will define a common structure that includes the common interface, but for each one of them instantiated to their methods. And they will also extend it by adding additional fields. So here B has some field that can be controlled by the attacker, and A has some field that is a pointer. But now suppose, like in this example, that the A has this pointer control field. This means that if we can replace the interface's indirect branch with a collection of direct branches, then an attacker can train the branch to always call the method of the A subsystem, which happens to read from the pointer and maybe leak its value. And then if the attacker would execute the code again, but this time passing it an object of type B, then what would happen is that the indirect branch prediction would get mispredicted. The CPU would misspeculate. It would execute this method, which expects to get an object of type A, but it actually gets an object of type B. And so it would dereference this field that is controlled by the attacker, dereference an attacker controlled address, and again, leak its value. So again, this is a potential speculative type confusion vulnerability. And so to explore the implications of doing this type of Spectre V2 mitigation in Linux, we did a source level analysis on Linux, looking for potential polymorphism related speculative type confusion. I won't dwell on the details of how the analysis works. Essentially what we did is look at all function pointer invocations, see which of them can point find all the targets of a function pointer, look at each of these targets, see exactly which fields they use, which objects they derive, and then look at all pairs of legal targets and check for these types of overlaps like we had here, where you have two different legal targets of a function pointer, but one of them derives an object that has an attacker-controlled scalar, and the other derives an object that has a pointer and dereferences this pointer. And so we ran this analysis, and we actually found that if you look at all function pointers in Linux, then there are thousands of these cases. And if you limit them into potential risky cases where the value dereferenced by one of the legal targets gets, let's say, used as an array index afterwards, so it actually gets leaked, then you still have many of them, hundreds. But when you look at these hundreds, it seems like currently at least they cannot be exploited for various cases. So So we started with looking at these thousands of cases. A lot of them are simply not afterwards used as an array index. So we ruled them out. Out of the ones that were the red value, the reference value is used as an array index, a lot of them have an overlap between the two fields that is smaller than 64 bits. So an attacker cannot use the overlap to represent a complete virtual address, so it doesn't seem like it's easy to exploit. And then there are other cases where the attacker has limited control over the value and can't represent a kernel address, and some other cases. So with some superficial analysis, we think that currently these cases are not exploitable. But again, if something changes in the code, if somebody changes the size of a field or reorders field within an object, these type of changes, then these cases can be exploited. And so what this means is that although currently there is no problem because Linux is using red pollins, if they actually go ahead with their plans and change the mitigation approach to be this type of sequence of direct jumps instead of a red pollin, then the kernel security would be on very shaky grounds because you have thousands of potentially vulnerable cases, and any small change a developer makes might cause some code to be vulnerable to speculative type confusion attack. So in the interest of time, I won't go over an example, a specific example. I'll talk a bit about mitigations. So what can be done? What can Linux do? So the main thing is that using a manual mitigation approach like they currently do seems like not a good idea because it's very hard for programmers to detect all the cases they need to protect. The problem is that if there are complete mitigations, basically that the compiler can add to the code, which block all types of speculative execution attacks. One of them is called SLH, or speculative load hardening. But the problem is that they add a lot of overhead. So we did a benchmark and we saw that if you enable this SLH protection in Linux, you get about a 2.x slowdown for the system call. So it doesn't seem like this is currently a viable approach. And as I said, the current approach of doing manual mitigations is also not very viable in the sense that it's potentially insecure. So this is why we believe that the long-term solution is to have some hardware support in order to make these mitigations more efficient. The current status quo is not very good. And so to conclude, I've shown you that speculative type confusion vulnerabilities actually exist in the wild, and our analysis found both exploitable vulnerabilities and many latent or potential vulnerabilities. Speculative type confusion puts into question the manual spot Spectre mitigation approach like used in Linux. The relevant gadgets don't have a specific structure. They can insidiously materialize as a result of benign compiler optimizations and code changes. And this makes it very hard, if not impossible, for developers to reason about the code and manually apply Spectre mitigations. So the takeaway here is that Spectre Variant 1 is far from being limited to bounce check bypasses, and that fully mitigating it in software will be hard. So more research is needed, both on software and hardware defenses from Spectre. And that's it. If there are any questions, I will be happy to take them.
Yeah, thank you, Adam. If you have any questions, you can either paste it in the chat or you can ask directly. Okay. Right. So one of the questions I have is, it's to me, right? The problem is we are using a layered way of building the computer systems, right? So building CPU, building the operating systems, building the compilers, building the code, the program. But each layer, right? The developers, the hardware developers, right? they have a local view. So they do things which are not expected by the other people in the other layers. And that's actually create this problem. For example, this compiler actually introduced some vulnerabilities, but from the compiler developer point of view, there is nothing wrong. And if the CPU doesn't really use this speculative execution, it's actually okay, right?
Yeah.
So is there a way for people to have a global view of the whole thing, or is that something necessary to prevent this type of attacks?
So I think that the problem with a global view, it's all the complexity, right? At the end of the day, you don't want everybody to know all the details of all the layers of the stack. And that is why we have these contracts. There is the CPU has a contract, the instruction set architecture, which is a contract to the software. The compiler has a contract with the programs. The problem is the speculative execution attacks is that there are optimizations that due to implementation artifacts can lead to the contract breaking in some sense. So it's not really that it breaks, but some implementation details of the CPU can be observed by running programs. And so I think that a better approach would be to just, and there is some research on doing it, to either strengthen the definition of the contract. This is one possible way. It's essentially a fancy way of saying maybe the compilers should consider speculative execution when they do optimization. So that is one approach.
Yeah.
Or the hardware implementation should be strengthened so that it enforces the contract better and doesn't let the result of speculative execution lead to disclosure of memory.
Yeah, but so one of the things is like all the contracts, right? When we actually make the contract, we don't know all the possible consequences or situations. So there's always something we can't expect. For example, when Intel implements this speculative predictions, right? They didn't really break the contract, I guess. They just introduce something which are not specified by the contract.
Well, yeah, they didn't break the contract. What happens is that the optimizations that they make can be observed by the program because of essentially if you look at the core reason, it's because the contract, the specification has some non-determinism.
Yeah.
So for example, if you look at timing instructions, you cannot specify them in a deterministic way. So a program can run them and figure out some memory access is slow, some memory access is fast, and use that to infer things.
Right.
So you could look at places where specifications have non-determinism and focus on them. And you can also, there are a lot of CPU optimizations, but not an infinite number of them, and a speculative execution is a major one. So you could try making that more secure. I'm not sure that you can make a CPU that has no side channels, at least not without.
Probably not possible.
Yeah, exactly. But I think that the dangerous thing about speculative execution side channels is that, unlike, let's call them traditional side channels, they give the attackers the ability to read from arbitrary memory locations. Previously, people knew about side channels, but you could leak content of registers for specific programs. So if you were writing cryptography code, you had to be careful. But now it's suddenly something that can affect, you just saw the operating system, which is a huge amount of code. That is why it's more dangerous and maybe worth to looking at the way the optimization is implemented and trying to mitigate the types of leakage that it can lead to. So there's actually quite a bit of research on doing this, building hardware that does speculation, but does it in a safe way.
Right.
And I hope that some of it gets adopted by industry and improve the situation.
Yeah.
Because the current solution of telling software people, add mitigation, that seems like a very unsound way. It's not hard. It's not easy for a developer to figure out where to place mitigations.
Right. There is a question from Roy. Roy, do you want to ask the question yourself?
Thanks. Maybe the question has been answered by the answer to your question, but my question that I have in the chat is just, is there anything that can be done to eliminate the kinds of vulnerabilities that you've talked about? And what a great talk. Thank you.
Thank you very much. Maybe I'll just add a little thing is that you can break it down into, you can have software mitigations, which I talked about. Currently, there exist complete mitigations, just they add a lot of overhead. There are proposals for hardware mitigations, but they're not deployed. It's just research at this point. And maybe there is also a direction of doing some kind of hybrid. So having a software mitigation, but using some type of hardware optimizations or hardware support to make the software mitigation more lightweight and imposing less overhead. I think at this point there's no like good solution which is both sound from a security perspective and very efficient that can be used today. You either have to worry that maybe you miss some cases, or you have to pay the performance penalty. And my argument basically is that I hope that CPU vendors will kind of step up a bit and consider making the CPUs a bit more secure, add support for mitigations, so that it's easier for the software ecosystem to handle these types of issues.